So, hello guys, sorry for the rain. Rain is falling, but I will increase my voice as much as possible so that my voice can overcome the sound of the rain. So, we want to talk about fluid dynamics. Fluid dynamics. Okay, I will use the earpiece rather. Sorry, I have earpiece. Sorry, the earpiece is not so. Moving fluid, when fluid, the word dynamics means it's not in a static position, it's moving. That's the meaning of dynamic. So moving fluid is described by the flow of velocity. The flow of velocity, that is what we use to describe moving fluid, like a fluid that is moving. The fluid could be gas, yeah, it could be air, it could be liquid, it could be water, it could be kerosene. When we are talking of fluid, we are not just talking of liquid. Gas is also a fluid. Are we together? So moving fluid, that's why we use fluid generally. Moving fluid is described by the flow of velocity at each point in the fluid. If you have like this diagram I draw here, at each point in the fluid, this is the flow of velocity. At each point in the fluid and at each instant of time. Instant, when we talk of instant, it's a instant means at that particular point, at each point of time, at each point in the fluid, at each point of time. When you have a flow like this of liquid, and from here to here, let's say the time between is 3 minutes. At each point, at each instant of time, or at each point in this fluid, at each point, and at each instant of time, there are billions and trillions of instants of time that we can get in 3 minutes. I hope I'm making sense. There are trillions instants that we can get in 3 minutes. So at each instant that we are talking about here, in fact, for us to calculate something like that, we'll be dealing with calculus. But that's not our business for today. We are just dealing with definition. So moving fluid is described by the flow of velocity at each point in the fluid and at each instant of time. That's why you see the formula, there is something like per seconds. That's when we are talking of rates, because here we are also dealing with time. Now note, when fluid, where's my duster? Sorry, I'm coming. When fluid flows steady, what do we mean by steady? That is, when fluid is flowing uniformly, when it flows steady, the fluid motion, okay, the fluid motion pattern, that is the pattern of the fluid motion, is constant. Whenever a fluid is flowing steadily, the pattern of the motion of the fluid is constant. What do we mean by that? It is the same at each point. Are we together? So related to this diagram, what we mean is that now, here now we are talking of rates. How do you know we are talking of rates? Because initially I mentioned time, per time. That is the rate of flow of liquid at each point. Am I communicating? So, and that fluid is a matter, so it's going to have mass. Am I communicating? So that's why we are dealing with something like how can I put it now? The quantity of the fluid, quantity, and in the sense of quantity now we are talking of mass. So the quantity of fluid that is flowing, the rate of the quantity is known as what? Gravity, area, and volume. This is the quantity of the fluid that is flowing per time. This is the rate of the quantity. Let's see whether it's true. Density, area, and volume. Density is mass over volume, abi, times what? Area, abi. Sorry, velocity, not volume. I'm sorry, velocity rather. Density, area, and velocity. Am I communicating? So mass over volume times area. Velocity is what? Meter per second, right? I know volume is meter cube, isn't it? Area is meter square. So meter square times meter, that's meter cube. It will cancel meter cube. What do we have? Don't let me put kg here. Mass over meter cube. What do we have left? No, the velocity is meter per seconds. Area here is meter square. Meter square times meter, meter cube. It cancel this volume. So here we have kg per seconds. So the rate of quantity of liquid, the flow of quantity of liquid is known as what? Density, area, and velocity. With the unit of what? Kg per seconds. So like we discussed earlier, this rate is constant at each point. So that's why we have this guy to be equal to what? C. Are we together? So if it's constant, we can say at each point, A1 velocity 1 equals to what? Density 1, density 2, area 2, velocity what? Velocity 2. I hope I'm making sense. Now, C is the constant along the flow tube. Am I communicating? Why this one is the density of the fluid, this is the velocity of flow, and this A is what? The cross-sectional area. Am I communicating? Now, the next thing now, what have I not touched? Let me check. Okay. I'm thinking of moving to Bernoulli equation, but I'm checking something if I've not skipped anything. Okay, no problem. If I will remember, I will come back. So now, Bernoulli equation now. Oh, yeah, I remember. Now, what we just did this earlier, that's P1, A1, V1 equals to P2, A2, V2. It means that what's it called? It's called the continuity equation. It's called the continuity equation. That is, the equation is continuous at each point in this flow. It does not change, it's constant. Are we together? And this verifies the law of conservation of mass. You know, the unit, this density, area, and velocity, the unit is kg, is mass, but we are talking of rate of quantity. That's why we have per second. So this is law of conservation of mass. You can say a question there. What is it talking about? You should know it's talking about what? Law of conservation of mass. But note, in a steady flow. If the flow of the fluid is not steady, then mass probably may not be conserved, or PAV may not be constant. This is constant because of what? The flow is what? Is steady. So that's that for that. Now, the Bernoulli equation. Now, the Bernoulli equation is a statement of conservation of energy. The continuity equation now is what? Conservation of mass. Continuity equation, we use that one as conservation of mass. This one, conservation of mass. But for Bernoulli, it's conservation of energy. Sorry. Bernoulli is conservation of energy. Now, how do we deduce this? Now, take a very good look at this diagram. Take a very good look at this diagram. If we have a flow of liquid, maybe it's flowing from here to here or from here to here, there is no problem. There is a force here, a pressure that is pushing, and that pressure has a force. A pressure that is pushing the liquid to be able to flow, whether down like this or up like this. And that pressure has a force. We call it pressure force. So at this point, we have our F2, which is, if pressure equals to force over area, if we cross multiply, force will give us pressure times area. That's what we have here. F2 equals to P2A2. Same thing at this point, there's another force, pressure force, equals to P1A1. Is that clear? So here now, here because we are talking of at each point, we are talking of instant. That's why you are seeing dx here. That is a very small change in this length. That at each point, we have a constant. So if you want to calculate everything together, that's, how can I put it now? Whenever we are talking of instant, that's where you see the issue of dx, that is changing So that's not even our focus now. That's not even our focus. Now the height of this liquid to ground level, we call it H2. The second part, the lower part, we call it H1. Now that conservation of energy, the formula we want to derive now. Take note, the step one. Just understand it's not hard. For step one, we have what's it called now? How can I put it? Okay, before then I remember something. You know, because the liquid is flowing. Okay, I will still come to there. Don't worry, I will still come back to it. Now step one, work done by pressure. No, a pressure is pushing the flow. It's pushing the liquid. The pressure is doing the work. The work done by pressure is what? First of all, you know that pressure equals to what? Force over area. If you cross multiply, force will give us what? Pressure times what? Pressure times area, right? You know what we need is work done by pressure. And what is work done? Work done equals to what? Force times distance. And what is our force? Pressure times area. So work done will give us pressure times area times what? Distance. Isn't it? That's our first step. That means our work done equals to pressure times volume, because area times length or times distance is what? Volume. So our work done equals to pressure times what? Pressure times volume. There's something I'm trying to remember. I'm trying to remember something. Okay, before then, now because we have what is it called? We have P2 here, we have P1 here. According to this, so here we can say our net work done. Why? Because the pressure work is entering. Pressure is entering. Pressure is also leaving. So we have P1 and P2. So we can say this is P1V minus what? Let me say minus P2V. Whether P2V minus P1V or P1V minus P2V. So this is our network. So, and don't forget, we all know that, okay, let's factor out volume. At the end of the day, we have volume equals to what? We have work net equals to P1 minus what? P2. I've been shouting, so the rain is getting better now. So I think you can hear my voice now. And don't forget, under density, you know, density equals to mass over volume. If you take volume, the side of the formula, that means volume equals to what? Mass over what? Density. So here you can conclude that our net work done equals to what? Mass over what? Density into what? P1 minus what? P2. I'm deriving this formula so that at any question they give you at a particular point at a time, then you know what they are referring to, even though you are not going to use that equation you want to derive. Original, maybe you know the question given to you does not require you to use that equation. So anything they ask you, you can know what to do. Now our net work done now equals to volume, which is mass over density, times P1 minus what? P2. Now the next step, we also have kinetic energy. So you know it's a flow, so there is velocity. It's a flow, so there is velocity. Because there is velocity, there's going to be kinetic energy, which is 1 over 2 mv squared. But kinetic energy, we are talking of entering and leaving, so we are going to have change in kinetic energy, which is 1 over 2 mv, let's say mv2 square, m into v2 square minus what? V1 square. Are we together? Don't forget we have our W net to give us mass over density into P1 minus P2. Whether P2 minus P1, there is no problem. So we also have our net kinetic energy to be this. So our net kinetic energy to be 1 over 2 m into V2 minus what? V1 square. Are we together? No, here also we are also talking about height. So if you are talking about height, that means there is also what? Potential energy. So you know potential energy equals to what? mgh. And if you are talking of net potential energy, so our potential energy, change in potential energy or net potential energy is going to give us mg h2 minus what? H1. So these are the three things we need. So potential energy now, our PE net equals to mg h2 minus what? H1. Are we together? So like I said, the Bernoulli equation is about what? Law of conservation of energy. And what's conservation of energy? The total work done equals to the total energy, isn't it? That's law of conservation of energy. And what do we have here? M over density into what? P1 minus P2 equals to 1 over 2 M into what? V2 square minus V1 square plus mg H2 minus what? H1. Since there is M on both sides, so this mass can cancel each other. Since they have common mass, like there is mass on the two sides, so they can cancel out. So what do we have left? What do we have left? We have 1 over density into P1 minus P2 equals to what? 1 over 2 into V2 square minus V1 square plus what? G H2 minus what? H1. Are we together? So this is what we have now. Now, let density multiply everything. So here we have P1 minus P2 equals, if density should come here, what do you have? You have, I'm checking something. You have 1 over 2 density V2 square minus 1 over 2 density V1 square. This times this, you have this, plus this density that's coming up. Plus, if the density 2 should come here, you have density G H2 minus what? Density G H1. What I just do is cross multiply. This one will come here. You know, these two in bracket, you multiply density, then you open this bracket, you get all these things. So here you have what? P1 minus P2. Sorry now. You know, this equals to this minus this. So now you now have P1. This one I have 1 negative, bring it to the other side, plus 1 over 2. Sorry, this is P. Let me not make it look like density. Plus 1 over 2 density V1 square. What else do we have? This minus, if it comes to the other side, it becomes plus density G H1 equals to, no, this negative P2. If it comes to the other side, it becomes P2 plus 1 over 2 density V2 square plus density gravity H2. So this is the Bernoulli equation, law of conservation of energy for a dynamic fluid dynamic. Do you get how we prove it? So I'm just proving it so that they can ask you questions based on each point. They may not even ask the question that they will ask you. You may not even need this to calculate. Maybe the angle we are coming from, all those changing work, changing those. It may be that formula you need. That's why I brought in all those stuff and use it to derive this final formula. Now I think I have a question here. If you don't understand, please drop a comment section. No problem. I think I have a question here. The question, let's say we are given a particular question. I don't really have time. Maybe you have your P1 equals to 2 times 10 raised power 5 PA, and you're also given V1 equals to 2 meter per second. Are we together? And you're also given V2 equals to 5 meter per second. Maybe you are given H2 to be equals to H1, and the density of water equals to 1000 kg per meter cube, and you're asked to find P2. Is that clear? You're asked to find P2. Now, since H2 equals to H1, this one, H1 equals to H2, and gravity is the same density you are using. So you know these two will cancel out from each side. So what do you have left? P1 plus 1 over 2 V1 square equals to P2 plus 1 over 2 V2 square. Why? Because density gravity H1 have cancelled density gravity H2. If it comes to the other side, they cancel out. Since density of water remain the same, gravity remain the same, and H1 equals to H2, they cancel out. So this is what you have left. Then put in your value and find your P2. That's just it. If at any point I've misplaced density with P, please pardon me, just know the difference. And if at any point I've misplaced volume with velocity, pardon me, but you should be able to deduce all of that. So that's just it. Thank you for watching. Don't forget to like and subscribe.